Oh man, cucumbers are like the least attractive vegetable. I'm not crazy about cucumbers. Okay, well, welcome to our test review. It is not about cucumbers. It's actually about chemistry. That's okay. Chemistry 1405, Test 4 review. We'll be covering chapters 8 through 10 and focusing on the questions which you all specifically have. Now, here's the deal. We are not going to necessarily have time to go through the entire test, so let's focus on the questions that you feel like you most benefit from going over. And we'll kind of start from there. And if you also have any questions from your professor, from a test or quizzes or anything else that you'd want to go ahead and throw up there, I'm happy to take those as well. Cool? All right, let's dive into this. So, does anybody have some questions they'd like to go ahead and start with? Or should we just kind of start from the beginning and go? What do you think?
Do you think you'd be able to like break down the basics of what we're doing? Because I'm still kind of stuck at the very start of things. Like at the moment, I feel like I get something.
You have to move to the next one.
Yeah.
Okay. Well, so here's the when you say the basics. So what do you mean the basics of what?
Like I understand the atoms and bases, like the H3O plus that whole thing. But when it comes to 9 and 10, I know how to draw it. The organic chemistry part. I know how to like draw it. But other than that, I'm somewhat aware with like the carbons and all that. But
like the naming.
Yeah.
Like the naming's a pain.
Naming most important, and then well, I mean that's all.
Naming
yeah, that is nice. So yeah.
Gotcha. Yeah, no, that's totally fine. So let me kind of maybe open up to a mostly blank page. I'll kind of switch to the end here. Basically, when it comes to the naming, there's three things I want to share with you. Specifically, what you want to be aware of is the levels of priority. Oh yeah. What? Oh yeah. Let's dim this. Can you see it better now? Okay. So, I got people waiting in the lobby. Oh wait, what did I do? Okay, hold on just a second. But yeah, oh, so okay. They're letting. Okay, great. So basically, we want to look at what's referred to as the levels of priority, and the levels of priority essentially refer to what is when you're numbering the carbon chain. Which side do you start numbering from? Where do you start numbering from? Because that's the tricky part, and it's not always obvious. So the first thing you want to keep in mind is the first level of priority is the functional group. So you always start numbering from the side closest to the functional group. It doesn't matter if there are other branches or substituents that are closer. You always go with the side that's closest to the functional group. So what are some functional groups? Like that would be like an alkene, in other words, a carbon-carbon double bond, alkyne, carbon-carbon triple bond, an OH, an SH, different things like that. So anything that would be like one of those functional groups in that table of like 12 of them, you're always going to start numbering from the side that's closest to the functional group. So next is if there is no functional group, in other words, there's just a plain alkane, or if the functional group is in the middle of the molecule, so that it doesn't matter which side you start numbering from, then you number in such a way as to give you the lowest number on the first branch or substituent. Branch, not block. Okay. So, lowest number on the first branch. Now, of course, if you have multiple branches and it's the same lowest number for the first branch, then you go to the second branch. If it's the same for the second branch, then you go to the third branch, etc., until there is a difference, until one of them is lower than the other. You do rarely get certain cases where even looking at the numbers, it doesn't matter which way you number because you'll still get the same numbers on branches. In that case, what do? You go to the third level of priority, and the third level of priority is, in fact, alphabetical order. So you number in such a way as to give the alphabetically first substituent based on the name, to put that, as it basically put that first, or number that, give that the lower number. Get the lower number on the alphabetically first substituent. So let's take a look at a couple examples to kind of like bring this illustration to point. Let's say I have, let's minimize this. Let's say I have something like this. I'm going to draw something. Okay. We'll put this here. And then we will put a bromine here. And maybe we'll even put a methyl group here. Okay. So if you were going to number this, you would want to start, look at the levels of priority. Which side are you going to start numbering from? Am I going to start numbering from this carbon here or from this carbon here?
From the right. I would think the right side would be broken.
Actually, you have to start numbering from the left. Because the first level of priority is the functional group. If I number this, and I'll go ahead and show it, if I numbered it from the right, the number that I would give the double bond, which is the functional group, would be 3. Because with double bonds, the double bond is always between two numbered carbons, and you always give it the lower number. So since the double bond is between 3 and 4, you would call that 3-pentene. However, that is not the best way to do it, because if I numbered it the other way, 1, 2, 3, and this is my orange, 4, 5. I get the double bond is between carbons 2 and 3, and I would call this 2-pentene. Now, even though the substituents, the branches, have higher numbers, the branches are not as important as the functional group. So then, therefore, the name of this compound, based on this. Now, of course, one of the things I like to do is I like to circle anything that's not, or put a square or something like that, mark anything that's not part of the longest chain. So let's get a good bright color here. How about this one? So this bromine is a branch off the main chain, and this methyl group, this one carbon group, is off a branch. So I would actually call this guy, well, the root name would be, of course, 2-pentene, but then I have to go back to the beginning and put the branches in alphabetical order. So when you're naming it, even if the numbers, even if they're not numbered in alphabetical order, they're named in alphabetical order in the name. So in this case, 5 is the bromo. Bromo comes before methyl. B comes before M. So this would be 5-bromo dash 4-methyl. Okay, so and part of this is just coming down to like knowing the names of the first 10 alkanes. But essentially the first 10 alkanes, a 1-carbon alkane would be called methane. And a 1-carbon branch, if it's the main chain, it's methane. But if it's the 1-carbon branch off of a larger chain, it would be called methyl. The ANE becomes a YL. Same thing with ethane is a 2-carbon branch, or 2-carbon chain. If you had a branch off of a 2-carbon branch off of a larger chain, it would be called ethyl. The YL ending means that it's a branch off a larger chain. So the first 4 usually don't have branches that are longer than 3. So usually it's a methyl, ethyl, or a propyl branch. But as far as the names of the chains, you're kind of supposed to know what the names of the first 10 alkanes are. Yeah. So methane, ethane, propane, and butane, these are the hardest ones to remember because there's there's nothing explicitly about the term meth that tells you that it should be 1, you know, or eth that tells you it should be 2, or prop that tells you it should be 3, or but that tells you it should be 4. But once you get to the 5th one, pentane, well, a pentagon is 5-sided object, you know. A hexagon is a 6-sided object, and you might remember like hexa as a prefix for like, you know, hexafluoride means 6 fluorines and covalent naming. So after you get to, you know, 5 and 6, it's pretty straightforward from there. Except, I mean, of course, hepta is a little bit weird, but even that you've probably seen before. That's 7, and then octane, 8. Nonane kind of sounds like 9, and then decane. So if you can remember the first 4, then you're good. 1, 2, 3, 4. Once you got the first 4, the rest are usually pretty easy to remember. So but yeah, so this one's 5-bromo 4-methyl pentene, and notice the numbers are not in order. It's the alphabetical name for the substituent that's in order.
So on number 4, I guess is it just 4, or is there a proper name for it? So I can tell you something. 4, right? That orange 4 is where that.
Oh, 4, yeah.
If there was a line that went down, it would be ethyl. If there was a 3rd line that went down, that would make it propyl.
If there was a line that went down from the 2?
No, from 4.
Oh,
Well,
actually, that's a good question. No. Because okay, now you're opening up a whole new can of worms, because the problem is you put a line off of that, you've changed the longest chain.
Oh, okay.
So 1, 2, 3, 4, 5, 6. Okay.
I take it back.
Okay. Yeah, and then you'd have to go into complex substituents, which honestly you're not going to see. But let's say you had something like that here, then that would be an ethyl group. So there'd be an ethyl group off 3 because, and then this would actually be a 5-bromo, or rather it would be a 5-bromo 3-ethyl 4-methyl 2-pentene. So you'd have to add that part to it, but yeah. But let's do another example. You up for another example?
Of course, I'd love one. Let me try to steal it from y'all though, because I feel like everyone has got maybe some. I know you do for a fact. Everybody uses that name. I never get to answer the question. You know, I'm always like.
Sorry, Ron, you told me.
And I don't ever have the right answer.
Never mind.
Mm-hmm. Okay.
1, 2.
Let's try and name this one.
6 carbons.
Okay. Okay. So you got the root name. Is there a functional group?
No.
Okay.
But the lowest number of first branch we would hit. It technically wouldn't matter because of how it's set up, right? Alphabetical. So we would go from right to left. The CO is Victoria.
You mean if you're saying right to left, that means you go.
My right. Oh, because.
So, okay. So you're saying so let me get this clear. You're saying that I should start counting from this side, right?
Yes.
Okay. Why is that wrong?
Because B comes before C. That's not wrong. Or it is wrong.
Because they're always closer.
What's the methyl is closer to the end. Remember, the second lowest level of it's the second level of priority is the lowest number. If there's no functional group, you have to look for the lowest number. See, if I numbered it like this, but my branches would be on carbons 3, 4, and 5. However, if I was to number it the other way, my branches would be on 2, 3, and 4. Does that make sense? So my first branch would be on carbon number 2 if I numbered starting from the right, but my first branch would be on carbon number 3 if I started numbering from the left. So I have to go in which direction gives me the lowest number on my first branch. Cool?
Yeah.
Okay. So then what would the name of this be then? You said 4 bromo, 3 chloro, 2 methyl, and then hexane. I'm going to drag this over. Yeah. And that is correct. Notice that I always have to put a dash between numbers and letters. And I would also put a comma between numbers and numbers. So let's do let's do another one. Why not? Okay. Give you another chance to. Okay, let's see. Actually, let's do this. Okay. Which side would I have to number this from?
From the right to the left.
Right to left, why? Yeah, in this case,
We would do it this way because chloro comes before methyl.
yeah. If you numbered it the other way, you'd still get the same numbers. It would be 3, 4, and 5, or 3, 4, and 5. However, chloro comes before methyl. Chloro comes before methyl.
3, 4, 4 methyl.
What? So how would you actually say that then? 3 dash chloro, 4 comma 5 dimethyl.
Because there's 2 of them.
Mm-hmm. Heptane. Yep. So 3 chloro, 4, 5 dimethyl heptane. Make sense?
It would be wrong if I said 5 methyl, 4 methyl.
Yes. Yeah. Whenever you have 2 of the same type of group, you have to put them together. All right. Cool. All right. So you want to get to specific questions then? All right. So what question should we hit first?
I think we should do a few that's like like this one that's up there.
Okay. You want to start from the end and work back?
Sure.
Okay. And if anybody wants to go ahead and skip around, just let me know what question you want to jump to. Okay. Now it says, which of the following compounds would give a positive Tollens test? Now here's the thing. A Tollens test is a test for what? What will a Tollens test for the presence of?
You just learned that. Hydrogenation, right?
So a Tollens test is a weak oxidizing agent that will only oxidize what? Aldehydes. So I'm looking for the substance here that would actually be an aldehyde that I can oxidize. Which of these would therefore be an aldehyde? B. Butanal. That Al ending tells you it's an aldehyde. So this is butanal. Ethers can't be oxidized, at least not easily. Phenol can be oxidized, but you need a much stronger oxidizing agent. Methanol is an alcohol. Once again, you need a stronger oxidizing agent. And acetone can't be oxidized any further. So, because it's a ketone. So remember, to oxidize something, you need to have what's might be referred to as an alpha hydrogen. So an alpha hydrogen, like generally speaking, let's see here. So if I have a carbon that's connected to an oxygen, generally speaking, when it comes to oxidation in the context of organic chemistry, oxidation is generally thought of, at least for your level of oxidation, and even more generally, as an increase in the number of carbon-oxygen bonds and a decrease in the number of carbon-hydrogen bonds. So if I have an alcohol, okay, and let's say I have, let's say it's a primary alcohol. Primary alcohol means that the carbon connected to the OH is only connected to one other carbon. And then this might be connected to others, but I don't care. Okay, so what happens in the context of oxidation is that there is an increase in carbon-oxygen bonds. Carbon forms another bond with the oxygen. Now, oxygen only ever wants to have two bonds. So if it forms a second bond with this carbon, this hydrogen goes away. Furthermore, carbon can only have how many bonds? 4. Right now, it looks like it would have 5 around it. The only way you can add another bond to an oxygen is if you have an alpha hydrogen. So this carbon here, the one that's connected to the OH, it has a special designation, sometimes referred to as the alpha carbon. The alpha carbon, the first carbon, the carbon closest to the functional group, okay? An alpha hydrogen is a hydrogen that's attached to that alpha carbon. So basically, if I want to create another bond to the carbon from the oxygen, I have to kill one of these bonds. I have to get rid of an alpha hydrogen. And so that ends up leaving you with this product, which is a carbon double bonded to an oxygen, but it still has a hydrogen attached to it, right? And then it's connected to that one other carbon, which might be connected to a bunch of other stuff. Now, this aldehyde is actually tends to be fairly reactive and fairly unstable, so this can be oxidized further, but to create another bond to oxygen, I would have to remove this last. I have to have an alpha hydrogen that I can remove. Fortunately, I have an alpha hydrogen that I can remove. This can go away, but keep in mind, you can't actually form, you generally won't form more than 2 bonds to oxygen. So if this is going to be a stable compound, I have to make a bond to a new oxygen. And of course, a new oxygen is going to want 2 bonds. So if it has 1 bond to the carbon, that also means it's going to have to have another hydrogen there. So that will turn this aldehyde into a carboxylic acid. I don't know how much, I don't know if you needed to know that at all or not. So, but yeah, so that's how I figured it was important. But so that's how oxidation works.
Because the first one is okay, the last one is tertiary.
Well, this is the primary carbon in each case. Primary carbon, it means it's only bonded to one other carbon. And specifically in this case, here's my one other carbon, so my +1. Okay, so the alpha carbon is bonded to 1 carbon. In each of these cases, so it's primary. Only primary alcohols can become carboxylic acids. If this was a secondary alcohol, notice that if it's a secondary alcohol, I only have 1 alpha hydrogen, exactly. The number of alpha hydrogens tells you the number of times it can be oxidized. Yeah. In terms of the alpha hydrogens, yes. So a primary, it's called primary because it has 1 carbon connected to the alpha carbon. Secondary means 2 because it has 2 carbons connected to the alpha carbon. Tertiary has 3 carbons connected to the alpha hydrogen, or connected to the alpha carbon. But it's, yeah, the number of alpha hydrogens tells you how many times it can be oxidized. Any questions on that? We're good? Okay. All right, so next question says thiols can be oxidized to, so this is a weird one. This is kind of like just one of those equations you have to memorize. But thiols can be oxidized into something called, does anybody know? Disulfides. So here's your thiol group, it's connected to a carbon. Here's your, this connected to a carbon. Thiols can be oxidized into disulfides, and this is actually really important for tertiary structures on proteins. So what happens is these H's go away, and instead the sulfurs bond with each other, and you get a 2 sulfurs or a disulfide bond. Okay. That says, what classification of alcohol undergoes oxidation to yield a ketone? Secondary, yep. Because ketone is just one level of oxidation, so that would be one of these guys, a secondary alcohol. It says, what is the product when this compound undergoes gentle oxidation? Keyword gentle. Gentle oxidation means it'll only be oxidized once. If that's the case, what kind of functional group will we get?
So right now we have
What did you say? I didn't quite hear what you said.
Secondary?
Is this a secondary? So where's my alpha carbon? So this is my alpha carbon, right? How many carbons is it connected to? 1. So this is a primary alcohol. If it's a primary alcohol, when it is oxidized, that means I'm going to form an extra bond to oxygen, which means this hydrogen goes away, and one of these hydrogens goes away. So I'm going to have one of these guys at the end. What's that called? Aldehyde, exactly. So then how would I name that as an aldehyde? I'd have an Al at the end. So that rules out B and D. Now, what's the longest carbon chain in this compound? 4. The longest carbon chain would be 4. And the aldehyde is going to be right here. It'll be an aldehyde. So if I'm going to number the carbon chain, which side do I start numbering it from? Yeah, from the right side, because I have to start numbering from the side closest to the functional group, which means that these methyl groups here and here are on carbon number 3. So what's the correct answer in this case? It'd be A, yeah. 3,3-dimethyl butanal. Any questions? Oh, I'm sorry. Cyclo? I'm not sure what you're asking. Yeah, please do. Please write it down. I'm also a little bit deaf, so, and obviously the headphones don't really help, so.
you asking to see an example of a cycloalkane?
Cyclohexene. Oh, okay, yeah, no, that's actually a good example. Okay. So the gentleman here was asking, how would you go about naming a compound like that? That's basically how would you go about naming a compound that was a cycloalkene, like for example this guy here, and he drew this as an example. Well, what you have to recognize about cycloalkenes is that the functional group always is listed as number 1, and with cycloalkenes or cycloalkynes, the functional group is the double bond or triple bond. They actually have to always be carbons 1 and 2. So you might be tempted to try to do something like this. You might be tempted to say, okay, well, I know the double bond has to be carbon number 1, but I want the lowest number on the branch, so I'm going to number it like this. But the problem is you cannot do that, because carbons 1 and 2 must be the double bonded carbons. So since this is not an option, you can't make those 1 and 2. The only thing you can do is make this carbon 1 and 2 this way, or you can make it carbons 1 and 2 this way. I'm going to erase the 2 over here. Now, which one will give you a lower number on the carbon?
Purple.
Yeah, because if I number with the orange, it's going to be 1, 2, I think that's orange anyway. 1, 2, 3, 4, 5, 6. Chlorine will be number 6. But if I number with the purple, and I'm so glad you told me that was purple because I'm colorblind and I actually didn't know. This will be number 1, 2, 3. It'll be 3-chlorocyclohexene. And you don't ever actually have to put a number for a cyclic alkene indicating the location of the double bond or the location of any functional group really on a cyclic compound, because the number for the functional group on a cyclic compound is always going to be 1. Because a cyclic compound, a cyclical compound, can start anywhere. You can start your number from anywhere. It doesn't have ends like a linear compound would. And therefore, this would simply be 3-chlorocyclohexene. And that's it. Cool. All right, let's hit some more examples. And my online friends, you guys are welcome to go ahead and ask me questions too. Please do. I don't want you to feel like you can't ask questions. Okay. Now, 3 functional groups on this compound are what? So what are some functional groups? I actually see 4 functional groups that are present in this compound. Let's see if y'all can identify them.
The alcohol stop.
Okay. So there is an alcohol on the top. Very good. What's this one on the bottom called? What'd you say? Yeah, it's an ether. Yep. So you have an alcohol on the top, you have an ether on the bottom. All right, what other functional groups do I have? Is this an aldehyde? It's a ketone. See, and for it to be an aldehyde, it has to be at the end. In other words, it has to have at least one hydrogen attached to it. In this case, it has 2 carbons attached to it. So this would be a ketone. I'm actually going to type that here before I circle it. And then there's one other functional group.
Double bond 1 and 2.
So yeah, so this would be alkene. So which of these answers is correct? A. Strangely, none of them mentioned the alkene, but that'll work. Okay, next. Which of the following compounds contains a ketone functional group? What do you think?
Definitely either D or E. Just rule out everything else.
Ketone has a carbonyl, C double bond O, yep.
Don't need to worry about it.
So which one is the ketone, which one's the aldehyde? Yep.
So H on the end doesn't mean anything for this one?
The H on the end does mean something. H on the end means it's an aldehyde. The double bond O is always at the end. It's the double bond for an aldehyde. The double bond O is the last carbon in the chain.
Am I just silly, or is there not an H on the end of?
But that's attached to a carbon. It's not attached.
Mhm.
Oh, which is by
It's just
itself.
an H.
Yeah.
Okay. That's the difference between an aldehyde and a ketone.
Yeah,
Technically, it's connected to
yeah, yeah. The key thing is that the double bond O is attached to the last carbon in the chain, or rather, actually, the first carbon in the chain, the number 1 carbon, because you'd always start numbering it from there. See, if you look at E, you'd have to actually put a number 2 on that, wouldn't you? The double bond O would actually be a number 2. That tells you it's not an aldehyde. Aldehyde always has number 1. That's an easier way to look at it, perhaps. Ketone. All right. Next, the skeletal formula represents what type of alcohol? What do you think?
Okay, I'm gonna be honest with you. I see no hydrogens on there at all.
That's because skeletal formulas don't show hydrogens. This is why you got to look at carbons.
I'm gonna go with 1, 2.
Nope.
no,
Before you say anything, I'm going to give a little hint, okay? So whenever you see these skeletal formulas, what I recommend you do is write a little dot where the carbons are, okay? So you have carbon at every corner is a carbon, and every end is a carbon that's not, where it's not listed, okay? In this case, there's an OH at the end, so this is not a carbon right here. But any ending like into blank space, that's a carbon, and any intersection point is a carbon. So now you see all of these little black dots are carbons. Okay. So which one is the alpha carbon? Is it this one, this one, this one, or this one? Alpha carbon is the carbon connected to the OH. So the carbon connected to the functional group, that's the alpha carbon. So how many carbons is that connected to directly?
1, primary.
Exactly. That's the easiest way to deal with that.
Secondary alcohol has hydroxyl group bonding.
So the hydroxyl is the OH, and secondary alcohol has a hydroxyl group bonded to a carbon with
2.
2 alkyl groups.
It's secondary, there's 2.
Yeah, an alkyl group is a carbon group. So basically, the hydroxyl group bonded to a carbon, that carbon that it's referring to is the alpha carbon. So that's your alpha carbon. And if it's bonded to 2 alkyl groups, 2 carbons, then it's...
With 19 being applied to 20, if you
Yes.
what I'm putting down,
Yeah,
instead of there being 1, somehow there would be a second one, another carbon connected to the OH, correct?
well, it wouldn't be a carbon connected to the OH. It's connected to the alpha carbon. Now it says this hydroxyl group is bonded to a carbon
So,
that's
like,
bonded to other
If
stuff.
there was like a line that went down, then it would be 2. With
Or you mean like a line that went up?
Or up or down, right? Or is that
Yeah.
the-
Yeah, if there's a line that went up and there's another carbon here, then yes, this would be a secondary alcohol.
I just wanted to like reference 19 and 20.
Mm-hmm. Yeah, when it says it's bonded, the hydroxyl group is bonded to a carbon, that means that carbon is the alpha carbon. And then it says, well, that alpha carbon is bonded to 1 alkyl group, 2 alkyl groups, or 3 alkyl groups. In this case, it's a secondary alcohol, so 2. All right. What's the common name for this compound? With ethers, you can cut the compound in 2. They actually get named a little bit differently than other compounds. you can cut it into two pieces, the pieces on either side of the O. And then you name it each side like a substituent, like a branch, right?
Can I give a shot at it?
Yeah.
Yeah, not ready. I've got the ethyl part.
Okay.
Obviously, there's two. You taught me that today.
Yeah. So this is going to be an ethyl.
And then there's 1, 2, 3, 4, 5. Okay, I think I'm ready.
What is it?
Cyclo, because it's close to the ring, right?
Cyclo what?
Cyclo, pentyl, ethyl, ether.
Yes. Cyclopentyl. Normally a 5-carbon ring would be cyclopentane.
Told me Dr. Mo takes ether.
Normally a 5-carbon ring would be cyclopentane, but because this case it's a branch off of a larger, or we treat it as a branch because it's an ether, I changed the ending from ANE to YL. So cyclopentane becomes cyclopentyl, 2-carbon chain goes from ethane to ethyl, and then you put them in alphabetical order. Cyclopentyl, ethyl, ether.
I don't know if this matters or not, but is ether always at the end, or does
Ether's always at the end.
because he has it?
Now you put them in alphabetical order. You put them in alphabetical order. Cyclopentyl C comes first before ethyl, but there's 3 separate words. So that's another difference between common ether naming and the other types of naming that you might do. Most naming, you will only use one name for the entire compound using dashes or commas as necessary, right? In this case, it's more than one word. It's 3 separate words. There's ether at the end, and then there's the 2 branches attached to it. The 3 separate words. All right. 17, and what is the condensed structural formula for the product of the reaction with 2-butene and with water and a strong acid catalyst? Okay. So what's 2-butene look like? So usually, I'll just focus on the carbons first. Okay, and now in this case, then I'll add the hydrogens. Well, the first carbon is going to have 3 hydrogens because it only has 1 bond to carbon. This middle carbon already has 1, 2, 3 bonds, so it needs 1 hydrogen. This carbon has 1, 2, 3 bonds, so it needs 1 hydrogen. And the last one has 1 bond, so it needs 3 hydrogens. I'll just put CH3 here because I'm lazy. But basically, carbons always want 4 bonds. All right, so here's the thing. I'm reacting with water and a catalyst. Now, this type of reaction is called an addition reaction, and you probably have seen several of these addition reactions. One is hydrogenation. In hydrogenation, you add a hydrogen to each carbon, and the double bond breaks and turns into a single bond, and it turns into an alkane. That's hydrogenation. You then may have seen something like what's referred to as a halogenation reaction, and in which case maybe you have chlorine, so you have Cl2, and what happens is that this bond breaks, and one of the bonds here breaks, and you form 2 new bonds, and you get 2,3-dichlorobutane. So that's a halogenation reaction. Both of those are pretty easy because you're adding the same atom to each side, right? You're adding the same atom to each side. However, with a hydration reaction, that's a reaction with water, you'll do something similar, but it's going to be an H on one side and an OH on the other. So how do you know which side to put the H on and which side to put the OH on? Well, there's a little rule in chemistry called Markovnikov's rule in organic chemistry, and basically you can think of it this way: the rich get richer. So which carbon is richer in hydrogen? Is that one's going to get you the hydrogen. That one's going to get the hydrogen. Which carbon is poorer in hydrogen? That's going to get the OH. So The rich get hit richer. The one that's richer in hydrogen gets another hydrogen. Now in this case, each of these carbons is equally rich. Each of these carbons has the same number of hydrogen, right? So that means the carbon that's going to get the hydrogen is going to be either one. It doesn't matter. If you were, however, to have something like this, let's say you had a double bond here, and this carbon had 2 hydrogens, and this carbon had 1 hydrogen, and you had another carbon here, and you did this reaction, the H would have to go, the H that adds would have to go on the side with more hydrogen, and the OH would go on the side with less hydrogen. But I don't know if he's going to expect you to do that, or know that. I don't, has he gone over that?
I mean, it is the HOH, but
Not the
which side it goes on.
Okay, so then he's probably not going to bring that up. So my apologies, my bad. But it is kind of interesting. All right, so essentially what's going to happen then, as you probably have already guessed, is that the OH is going to add to one side, the H is going to add to the other, and the double bond is going to break. So this bond goes away. You get 2 new bonds here and here, and this bond breaks as well. And so I'll go ahead and erase that, and this is your new compound, 2-butanol. So the answer is E, yeah, or E. Cool? All right. 16. The hydrogenation of an alkene gives what type of compound? What'd you say? D?
Alkine, right?
Mm-mm. What'd you say? Alkane, B. B as in boy. Remember, hydrogenation adds hydrogen and breaks the double bond, turning it into a single bond. By the way, the hydrogenation of an alkyne gives you what? Gives you the same thing, an alkane. So a triple bond alkyne you can hydrogenate it, it'll give you an alkane. Double bond, hydrogenate it, it'll give you an alkane. The only difference is that with an alkyne, you add hydrogen, you add a H2 twice, and it kills both both extra bonds. All right. So which of the following pairs are cis trans isomers? And that's actually one thing that we didn't really deal with. How can you tell if something has a cis trans isomer?
So,
This is on the same side.
yes, like this.
What's on the same side?
The carbon. The things that are carbons.
Mhm.
We don't know. We just know the hand thing.
Okay, so basically, it comes down to this. Going back to our thing, really the name that we gave this compound, this one, the first one that we did, was actually not correct because it was missing a fundamental piece. It was missing, I want text. There we go. All right, I'm going to drag this over. It was missing a fundamental piece. And that fundamental piece was this. Whenever you have the double bonds of a carbon, whenever each double bonded carbon is bonded to exactly 1 hydrogen, so in this case, I have a hydrogen down here, and I have a hydrogen up here. Whenever each double bonded carbon is bonded to exactly 1 hydrogen, it's a cis trans isomer. Okay? Each double bonded carbon must be bonded to exactly 1 hydrogen. Now, if the hydrogens are on the same side, then it is
No, cis.
cis.
Cis is
If-
the same, trans is different.
Yep, and if it's on the opposite side, it's trans. And if you think about trans means across, so like transatlantic. So trans means that the hydrogens are across from each other. Cis means they're on the same side. All right, so going back up to this one, you're looking for each of the double bonded carbons to have exactly one hydrogen. Okay? So is A pair of enantiomers? I mean, a pair of, pair of cis trans isomers? Yes or no? First of all, does this even have double bonds? Okay, can it be cis trans if it has no double bonds? No. Cis trans is only for double bonds. There is no stereochemistry for alkynes. So X. All right. Now what about this one? Does the first compound have cis trans isomerism? No, because each double bonded carbon is not bonded to one hydrogen. So this does not. This one does. Each double bonded carbon is bonded to one hydrogen, but the first one does not. Okay, what about this one?
Yeah.
No.
No.
This has two hydrogens, not one. They have to each double bonded carbon has to be bonded to exactly one hydrogen. So, no, thank you. What about D? Yes.
Oh, check that out. Okay. Well, I mean, that's easy to remember. That's like one of those easy.
So each double bonded carbon has to be bonded to one hydrogen. The hydrogens are on the same side cis, opposite sides trans. This is a pair of cis trans isomers. What's wrong with E? Why is that not cis trans isomers?
Because the carbon, each carbon doesn't have one hydrogen.
Yeah, that's right. Yeah, this one has two, the other one has zero. So this is not cis trans isomerism. Okay, what about Iupac name of this compound? Number 14. Which side would I start numbering from?
Left. Right. Right to left.
Right to left?
Yeah.
Okay. Anybody else agree with that? You think left to right? What about you?
Oh wait, no, I take that. I go to right to left.
Right to left? Right to left?
I didn't see the double bond.
Yep.
Yeah.
And which one do I start with? Do I start with this one?
Well, yes, but no at the same time.
What do you mean no at the same time?
So I would start
No,
with that.
yes, you start with that. That one would be a methyl because it's not a double bond.
I actually don't start with that one because it's not the end of the chain. I have to start at the end of the chain. The longest carbon chain, remember, is going to be
1, 2, 3, 4, 5. Have dust, right?
yeah. See, like if my end carbon can't be bonded to two carbons, you know what I'm saying? I'm looking for a carbon that's only bonded to one carbon. That's going to be my end carbon. Okay, so this is going to be the longest carbon chain is 6. And so yes, then I will go ahead and number it. Change my colors. 1, 2, 3, 4, 5, and 6.
4, 5, methyl, dimethyl, 2, hexane, B.
Yeah, so it's going to be 4 chloro, 4, 5 dimethyl, 2 hexane. 2 hexene.
You did the four chloral first because of alphabetical.
Yeah, whenever your name, whoops,
Yeah, of course.
whenever you're naming, you always have to start your naming with in alphabetical order. Numbering doesn't have to always be in alphabetical order, but naming does. Okay, cool. What about the Iupac name for this compound? Which side do you start numbering from?
The right because of the double bond.
You got it.
Yeah.
So 1, 2. So what's the name here?
5 methyl, 1.
Okay.
5-methyl-1-hexene. Very good. E. Or E, rather. Sorry, I lied. E. We good? All right. Stop me if you have questions. Okay, which of the following pairs represent isomers? So isomers are compounds that have the same number of atoms of each type, but are arranged differently.
Did we talk about that?
I mean, we talked about cis trans isomers. Cis trans isomers are what you call GM. There's actually two types of isomers, and I probably should mention it. There is cis trans isomers, and those are also called geometric isomers. Cis trans isomers have the same connectivity. Same connectivity. What does that mean, connectivity? It means that the atoms are connected in the same way. In other words, the same atoms are connected to the same atoms, okay? There's also what's referred to as constitutional isomers. Constitutional isomers. Constitution is what something is made of, okay? Like the Constitution of the United States is what the United States government is made of. In other words, it's the framework that's made of. So like our Constitution would be like, you know, what we're made of, like essentially what gives us our framework or strength, etc. So Constitution is like how it's made up, okay? How it's made up. Constitutional isomers have different connectivity, which means the atoms are connected in a different way. But essentially, the root definition of an isomer is that an isomer is, or isomers are compounds that have the same number of atoms of each type, but are differently arranged somehow. Okay? Of each type, but are differently arranged somehow. Sometimes that means different connectivity. Sometimes that means a different geometric position. In the case of cis trans, the same atoms are connected to the same atoms, but they're forced to be in different places in space. Whereas cis, they're on the same side in space, and trans are opposite sides in space, and they can't switch from one to the other. Okay. In this case, you're talking about, in the cases shown here, we're talking about constitutional isomers. It means they have the same number of atoms of each type, but they're differently arranged. They're differently connected. Okay. So, is A a pair of isomers? No. This one has 4 carbons. This one has 3 carbons. Automatically ruled out. They have different numbers of atoms. Gone. What about B? Is B a pair of isomers? What do you think? B a pair of isomers? I have one yes. What do you think? Yes or no? Think they are? They are?
Because they're the same thing.
They are not isomers.
They're differently arranged somehow.
They're not isomers because they are literally the exact same thing.
Well, I thought they were just.
Okay. To be
Atoms.
even though they look like they're arranged differently, they're not actually really arranged differently. You know how you can tell? They would have the same exact name. Compounds that have the same name. If you think so this is the way you can check yourself. If you think 2 compounds are isomers, check and see if they have the same name. If they have the same name, then they're not isomers. They're the same compound. If they have different names, then they are isomers. Now in this case, this would just be 1, 2, 3, 4, that's butane. 1, 2, 3, 4, that's butane. Same name. Neither one has any branches, right?
We have 2 branches. We only have 1. Or the second part only has 1 branch.
Well, let's look at these. Let's look at this. Let's check the naming on it, okay? That's a good question. D looks like it might be the right answer. Let's double check. So the longest carbon chain and the longest carbon chain. So the longest carbon chain in each case is 4. They both have the same number of carbons and hydrogens, right? Now, which side am I going to start numbering the first compound from?
Yeah, that one.
Yeah, this one, right? This is going to be 1, and this is going to be carbon number 2. So this would be 2-methylbutane. Which side am I going to start numbering this one from?
Right to left. Dang it.
Carbon number 1? Yeah.
2-methylbutane.
2-methylbutane. These are the exact same compounds. They are not isomers. So E, yeah. If you look here,
Well, obviously, I mean, you can see it on that one.
Oh, well, it is,
Yeah, that's, I thought it was the same as you. That's the stuff.
yeah. All right, so, yeah, so in this case, yeah, 2, 3 versus 2, 2.
Yeah.
Yeah, and that was a tough one, but hopefully that makes it easier. Like if you're not sure, like obviously it's easy to see when they don't have the same number of atoms, but when they do have the same number of atoms, just check and see, is it the same name? Okay, number 11, what is the Iupac name for this alkane?
Okay, first things first, I'm going from left to right.
Well, first things first, you got to look for the longest carbon chain.
Okay.
How many carbons are in the longest carbon
1,
chain?
2, 3. Okay, sorry. Going right to left.
Well, the longest carbon chain is going to be this one, right? Did you see that?
Yeah.
Okay, that's the longest carbon chain. At this point, does it matter which side you go from? Yeah, it doesn't, because it's 1, 2, 3, 1, 2, 3. So it'd be 3, 4, or 3, 4. Either way you look at it, both branches are the same. So this is one of those rare cases in which you'll go through all 3 levels of priority, and it still doesn't matter. And if it still doesn't matter at that point, just pick one. It doesn't matter. There you go. What happened?
I was trying to do it. And you highlighted it.
Oh, I'm sorry. I'm sorry.
There you
I
go.
was so excited.
I stole your thunder. My bad. Okay, this one's all you, bro.
Okay.
This one.
You got this one hard. No help.
No help. I'm doing this all by myself.
Funny.
First things first, going left to right. Correct?
No, first things first, find a main carbon.
Okay, first things first, I'm going 1, 2, 3, 4. It's butane. Butane. You got 4 carbons and you got butane. And then I'm going from right to left because the chlorine on carbon number 1. See, I thought it would be, and then they're both chlorine, so it would be 1, 2, 3. Okay, A.
Nice. Let's go.
Yeah,
like, actually, it's
I would have walked out. I would have been so sad.
So 1,3-dichlorobutane. Very
I
good.
might not need to see you Saturday too then.
See, the key thing here is remember.
Chapter.
Remember, it's always start with the longest carbon chain. Start with the longest carbon chain. Then go through the levels of priority, number the chain, and then name the compound with the branches in alphabetical
I
order.
finally get it. No joke. That was the first one. I was like, okay, I got this one.
So complicated.
Yeah. Compounds that have.
Oh, look at this. Compounds that have the same molecular formula but different arrangements of atoms are called?
That's the only one
Yeah.
that is even
I thought it
properly.
was constitutional.
That's what I thought too.
Structural isomers and constitutional isomers are 2 names for the same thing. Yeah. Constitutional isomers, structural isomers. It's all good. All right, now we're finally into acids and bases. So
Lost me again.
So here we got an example of titration. It says 10 milliliters of 0.121 molar H2SO4 is neutralized by 17.1 milliliters of KOH solution. What is the molarity of KOH solution? So there's two ways to do this type of problem. There's the easy way and the hard way. Which way do you want to learn?
Easy way.
Okay. The easy way involves using what's referred to as the titration equation. Now the titration equation is similar to the dilution equation. It's the molarity of the acid times the volume of the acid times the number of H pluses in the acid. And that's equal to the molarity of the base times the volume of the base times the number of OH minuses in the base. That's the easy way. Okay, so what's the molarity of the acid here? So the molarity of the acid is 0.121. What is the volume of the acid?
10 milliliters.
Milliliters. And what is the number? How many hydrogens are in the acid? How many acidic hydrogens are there? 2. Now, not all hydrogens are necessarily acidic hydrogens. It's only the hydrogens that are in the front. So let's say, for example, if you had something like HC2H3O2, this would only have how many acidic hydrogens? 1. The hydrogens that are in the middle are not acidic hydrogens. Only the hydrogens in front, or if you see it written as a carboxylic acid, sometimes you'll see it written with a COOH. Hydrogens after a COO are also acidic, but usually there'll only be one hydrogen like that, and usually won't even see that. It'll typically just be the acidic hydrogens are in front. So that is equal to the molarity of the base, which we don't know, times the volume of the base, which is times the number of OH minuses in the base. Now, how many OH minuses are in the formula for KOH? 1. There's 1 OH minus, right?
What about the whole minus? Does that matter?
Well, see, remember it's an ionic compound, KOH, K plus OH minus, right? Yeah. So then all you have to do is divide both sides by 17.1 and 1, and then you'll get the molarity of the base. That's the easy way. The other way to do this is to write the balanced chemical equation for the neutralization of H2SO4 and KOH, and then use stoichiometry to convert the moles of the acid to moles of base, and then use the molarity formula to divide the moles of the base times the liters of the base. Yeah, so there's a lot more work here. Now, one thing to note here, the volume in this equation, the volume in the titration equation, can be, they can be different, or you can use milliliters or you can use liters, but you have to use the same unit. So for example, if one of them is milliliters and the other is liters, you're going to have to convert one to the other. They both have to be the same unit. It doesn't matter what unit that is. It could be gallons, it could be liters, it could be milliliters, it could be cups. Whatever the unit is, it has to be the same unit. Cool? All right. We're running out of time here. Well, technically we're kind of already over time, but that's okay. The H3O plus solution, H3O plus of a solution with a pH of 9.7 is?
That's that log thing.
So basically what it comes down to is, 10 to the negative 9.7. Basically, the pH, or rather, pH is the negative log of the H3O plus concentration. But if you're going backwards, if you're going from H3O plus concentration, it's going to be 10 to the negative pH. Yeah. So pH negative log of H3O plus and pH is the negative log of H3O plus. H3O plus concentration inversely can be solved for by 10 to the negative pH. Which is really the same formula if you know your logarithmic algebra, but if you're not as familiar with your logarithmic algebra, you kind of forgot about logarithms, then you might just want to memorize these separately. All right, cool. And if you do that, you'll end up getting like 2 times 10 to the negative 10. You'll need your calculator for that, unless you're like me and you're a genius. No, just kidding. All right. What is the pH of a solution with OH minus? So this is just a matter of, yeah, you have to use the OH minus to solve for the H3O plus. It's basically, 1 times 10 to the negative 14th is equal to H3O plus times OH minus. So just plug in the OH 1 times 10 to the negative 4th there, and then plug in the H3O plus, or plug in the OH concentration and solve for H3O plus, and then use the equation down here, take the negative log of the H3O plus. So 2-step process. And when is your test, by the way? Tuesday. Okay, good. I'll send out the review to you tomorrow then. I'm not going to worry about sending it out before I leave today. I'm not going to have time. So when a reaction is at equilibrium, which one of these is true?
Oh, yeah. No, A. No, that's not true. Don't even listen to me. A is completely wrong.
When it comes to chemical reactions, it's dynamic equilibrium, which means the forward and the reverse reactions are still occurring. It's just that when they're occurring at the same rate, so if products are going to form reactants and reactants are going to form products and they're doing so at the same rate, is the amount of reactants changing?
No.
No. The amount of products changing?
No.
No. But they're still going back and forth, right? Most of the equilibrium complex equilibria maintained in our body are like that. But if there's something to disturb the equilibrium, then those reactions are already going, so they can either ramp up in one direction or ramp down in the other direction or whatever. Now, which of these is strongest acid? This just requires you to know your strong acids. Do you know your 7 strong acids? You don't have 7 strong acids? What? No, 7 strong acids. I'm going to tell you what your 7 strong acids are. You better remember them.
Okay, I'll write them down right now.
Okay. So you have HCl. Actually, this is the hard way. I'm going to do it the easy way. Yeah, I'm going to type it. There. Okay. It doesn't matter. All strong acids dissociate completely, so it doesn't really matter which one is. Like, it's not like you don't really. I mean, technically speaking, one is stronger than the other, but it doesn't really matter in most cases. HCl, HBr, HNO3, oh, HNO3, I can't do the subscript, sorry. HClO3, HClO4, and H2SO4. So those are your 7 strong acids. Any other acid that you come across is going to be weak. There's millions of weak acids. You don't have to memorize them. Just memorize the 7 strong acids. Okay. Now it says for number 3, and then it gives you an answer of D, right? That's the only.
Base H2O would be.
It would be. For something to be a conjugate base of something, that means this thing has to act as an acid. So the conjugate base of H2O,
Has to be higher.
so H2O has to be the acid, and then the base is going to have 1 less hydrogen. So it's OH minus. If it asks you what's the conjugate acid of H2O, well, the conjugate acid of H2O means H2O was a base. And a base would mean it'd have to accept a hydrogen, so the acid would have 1 more hydrogen, it'd be H3O plus. Which of the following is correctly identified? HCl is a weak acid, CH is a weak base, NaOH strong base, etc., etc. C is correct. Yeah. HCl is a strong acid, calcium hydroxide is a strong base. NH3 is a weak base. Your nitrogenous bases are your weak bases. So nitrogen-hydrogen compounds, those are your weak bases. H2CO3 is a weak acid. So there you go. And last question. We finished the whole thing. Which one is following as a characteristic of a base?
Bases do not have a sour taste.
No, that would be like lemons, which are acidic, right?
Yeah. They do turn blue. No, that's acid turn red.
Acids turn litmus paper red. So that's not right. That's not right.
It's E. No. I doubt myself. No, yes. It is a base.
Yeah, this is correct. H3O plus in water, that's an acid. Now, is insoluble in water, is that a characteristic of an acid or a base? Neither. Trick question. Yeah. For something to be a good acid, it has to be soluble in water. For something to be a good base, it has to be soluble in water. So, yeah. Neither one is going to be insoluble in water. Cool. And that's not completely accurate, but as far as you're concerned, it is. So I'm just going to leave it there.
Thanks for your time, sir.
Yeah, you're welcome.
And I will see you around shortly after 10 o'clock in the morning tomorrow.
All right. Well, thank you so much for coming. I will catch you all later. Have a great evening.